Not that complicated. With Ava and Jacob.
Hi there, and welcome to Graphing with Ava. So here we have a question where we are given our function and our first derivative as well as our second derivative. Now these things you should be able to find on your own before you move on to curve sketching, but your teacher also might be able to provide them for you when you have a test because that's what my teacher did. If you're having any trouble finding these derivatives, just let us know and we'll make a video on that. But first, let's get into the curve sketching algorithm. So the steps for that is to find the domain, identify vertical asymptotes, horizontal asymptotes, and end behavior, then find the x and y intercepts, followed by finding critical points, as well as the intervals of increase and decrease. We also have to find the points of inflection, which is where the concavities will change, which means we have to find the intervals of concavity. And lastly, we take all that information and we sketch. So let's get started on step one. First, we have our function. Let's rewrite it over here. All right, so we're going to take that function and we're going to find when this function does not exist. This is how we find our domain. So when does the denominator equal 0? In this case, since we have an x squared plus 1, it will never equal 0. We'll end up getting an imaginary number. So that tells us there's never a point at which this function does not exist. With that said, we can now move on to step 2, which is finding the vertical asymptotes as well as the horizontal asymptotes. When we already looked at the domain, we realize that there is no way that the denominator will ever equal 0. And that tells us that there is no vertical asymptote, which means we can now move on to finding the horizontal asymptotes. So in order to do that, we should identify the 3 different cases that we can experience when finding that. So case 1 is when the degree of the numerator is less than the degree of the denominator, and that means that our horizontal asymptote is at y equals 0. Important thing to keep in mind is that your horizontal asymptote is about y and has a y location, meanwhile your vertical asymptote has a x location. So case 2 is when the degree of the numerator is equal to the degree of the denominator, and when that happens, your horizontal asymptote is a ratio between the coefficients. And lastly, we have case 3, which is when the degree of the numerator is greater than the degree of the denominator, and then we must do long division. So luckily we're in case 1, the easiest case. So that means that our horizontal asymptote is at y equals 0. But that doesn't end there. We now have to check the behavior around the horizontal asymptote, and this is called the end behavior. In order to do that, we must take the limit as x approaches infinity of the function. Now here you can see I'm writing infinity there, and infinity is a concept, it's not a number, but what we can do is when we write it down, we can identify what this infinity truly means to us. As you can see, we have an infinity squared on the bottom. This means that that number in the bottom is going to be insanely large, and it's growing at a rate faster than the top. This means that we are dividing a smaller number at the top by a really large number, and that's going to be approximately 0. Another important thing to keep in mind when observing the end behavior is the sign you'll get when you evaluate it. So in this case, we technically get a positive 0, and this kind of sounds a little insane, but the positive result just tells us that we are approaching 0 from the top, which is why we put it right at the top right corner of our number, because that indicates what direction we are approaching that number. We then have to decide what we're doing when we approach negative infinity because we have 2 sides of our function. Now I do the same thing here and I sub in the negative infinity into the x position. And here we get a negative result. That means that we are approaching 0 from the bottom and then we include the negative at the top right corner of our 0, just like we did previously. Now it's time to move on to step 3, which is finding our x and y intercepts. Now to find our x-intercept, we set y equal to 0, and our y-intercept, we set x equal to 0. First, let's start finding our x-intercept. So we write out our function again, and what I am doing is setting y equal to 0, So then I multiply both sides by our denominator, and anything multiplied by 0 is 0, and then we are left with 0 equals 3x, which just tells us that x is also equal to 0. On the other side, I do our y-intercept, where I then set x equal to 0, and since our numerator is equal to 0, that means our result is also equal to 0. With that said, we can determine that our y-intercept and our x-intercept are both located at 0, 0. Now we can move on to step 4, which is finding our critical points. In this step, we are starting to use our first derivative. So I'm just going to rewrite that for us. In order to find our critical points is when our first derivative is equal to 0. So that's what I'm doing here. Once again, multiplying both sides by our denominator, which then gets rid of it. And then I'm just solving for x using algebra. Now we can move on to the other stuff that we need to check, which is when our function doesn't exist. But we already covered in first step that there is no x value at which this function doesn't exist. But if we did end up having one, it would definitely change our function and how we graph it. Now what we can do is find our intervals of increase and decrease. Now this is very important in identifying which points are our maximum points and which points are our minimum points. Everyone does these charts a little bit differently, but this is how I do them. I write my x values at which the critical points exist at the top, and then I write every factor to the left. Now what I'm doing here is identifying when these factors are positive or negative, and this is how you can then identify if your total is positive or negative. Now the one with the squared on the outside of the brackets is always going to be positive because we know that any function that is squared is always going to be positive. Now the function on top of that, you can find out whether the function is negative or positive in between those intervals, between 0 and -1, -1 to 1, and 1 to infinity, by just plugging in any number you please onto your calculator. But the way that I like to do it is to visualize it graphically. And you can see me illustrating that over here. I draw a graph and I identify where its intercepts are, and then from that graph you can clearly see where these intervals are positive and negative. The next part of my interval chart is combining all of them. So I'm taking what the result of the multiplication would be. If you take a negative times a positive, you get a negative, and so forth. What I then do is that result ends up applying directly to our function. If a negative result occurs, then it's going to be decreasing. Positive result is increasing. And then what that can tell us is in our interval chart, we can easily identify which critical points are a max and min, because a min would occur from a decrease to an increase, and a max would occur from an increase to a decrease, which you can clearly see illustrated here. Our last step when finding the critical points is to find the y values of these critical points to make it easier when graphing. So that means we plug in our -1 and our 1 into our original function to find those values. Now we can move on to step 5. So step 5 is finding our points of inflection, and this is when our second derivative equals 0 or does not exist. So let's check when it equals 0. I'm rewriting our function here right now and setting it equal to 0, which means I can get rid of the denominator and just focus on the numerator. After solving algebraically, we get the result of x is equal to plus minus the square root of 3. Once again, we can formulate another interval chart where I include all of the factors on the left side. And this one is going to be important because we have a cubed root, so it's not squared anymore. And then at the top, I include all of our values at which our second derivative is equal to 0. And you can see that I also included 0 here. And although when we solved algebraically, we did not see that result, you can go then and look back and you see that I crossed out an x, which means technically I eliminated a solution. So if you do solve it in the way that I did, you have to keep that in mind, or you could have factored it differently than me as well. Now what I am doing is illustrating the graph. So first we have 6x, which is just a line, and you can easily identify which parts are negative and positive. Then we have x squared minus 3, which is just a parabola that is shifted downward by 3, once again making it easier to identify these intervals. And then lastly, we have this factor over here, which is an x squared plus 1 term, and although it is to the factor of 3, we know that x squared plus 1 is always going to be positive based off this graph that we illustrated. Now that we identified all of the intervals of our individual factors, we can then find our result, which ends up being what we see here. A negative is concave down and a positive is concave up. This can allow us to easily identify what points are our points of inflection, which is when our concavity changes, and then we can then check the y values in order to make graphing easier. So our last step is to sketch. Now over here I already created a graph for you to go based off of. You can create your scale however you would like, but you need to make sure that all of the values that are important are easily visible and identifiable on the graph. So what I'm doing here is going back to where we identified our critical points and their y values, and here we have two of them with a value of -3/2 and 3/2. So what I'm going to do is 3/2 is equal to 1.5. Sometimes I find it really easy to convert it to decimals because then it gets you a better idea on where to plot them. At -1, we are at -1.5, which I'm just going to put a dot there. And then at 1, we are at +1.5, and then I'm just going to put another dot. Now we're going to scroll back up and look at, are these points maximums or minimums? And we know that the one at -1 is a minimum based off our interval chart, and the one at +1 is a maximum. As you can see here, we already identified it back in that step. Now we can move on to identifying our points of inflection and where they are located on our graph. From our previous steps, we evaluated that our points of inflection exist at the x value of √3 and -√3. So over here to the top right, I'm writing what the value of √3 is, which is approximately 1.73. Once again, really important to write it out as a decimal to easily identify that point. Now in pink, you can see I am plotting that point right there. I have at √3, we had it as a value of 1.3, and at -√3, we had it at value of -1.3. So here you can see that I am locating that on the graph. Now I'm going to scroll up to go back to where we calculated our y and x intercepts, which is at 0, 0. And you're going to see that I'm going to plot them down in blue. Now we've gotten to the best part where we are able to actually take every information we have and put it all together. So here I am erasing those little curved lines and just attaching all of my points like so. Now, what we also have to remember is the pink points, which are our points of inflection, mean that it is changing concavity. So we're going from upwards to downwards concavity on the left, and then downwards to upward concavity on the right. Now, also, we can refer back to our end behavior and make sure that it is following that. And as we can see, we are approaching 0 from the top and 0 from the bottom when we are approaching said infinities. And that means that everything we have done on our graph is complete and correct. And now you know how to sketch a graph based off of one function. I wish you all the best and see you next time.
Thank you for watching Not That Complicated. Don't forget to like and subscribe.